Welcome to the introduction to the Mainframe CPU Architecture, so the architecture of the mainframe processors. My name is Philipp Brone from the Neu-Ulm University of Applied Sciences. The mainframe processor architecture from the beginning has been designed in a way that it is not just defined ad hoc, as it was used in these days in the 60s for other systems, but before the architecture was implemented, its principles were laid down in a document called the Principles of Operation. And this document is basically the description of the architecture. So it specifies registers, instruction set, I/O system, and everything related to the hardware. And this document has remained until today. So it has been a new version of the principles operation for every new generation of the mainframe CPU. And this document is public, so you can download and read it. And it in principle can be used to build a compatible system. This is sometimes used by emulation approaches as well. In the past it was also used by other IT companies that offered IBM-compatible mainframe systems. And it's very instructive to read this document because if you want to get a deep understanding of the way how this system actually works. So the principles of operation are basically the essential specification of the system. Over the years, the architecture of the mainframe CPU has evolved from the original S360 architecture, which was a 16 and then later 24-bit system. Here the number of bits refers to the width of the CPU internal data buses and registers. And then it was succeeded or superseded by the S370 architecture, which was first the XA, which was for the first time then a 31-bit architecture. And then this was again extended in the 80s to the so-called ESA architecture, which also was a 31-bit system, but with some special features to have more address space. And then it came up with the S390 in the 90s, and then later on with the Z. So you could see that whereas in the first version, the S360, the 360 was a synonym for 360 degrees, showing the unique or the possibility to use the system in nearly all kinds of applications. Then later on it became more like a number of the decade. So in the 70s it was 370, and in the 90s it was 390. In the 80s it was not 380, but it was 370, or just called the ESA architecture. And then in the new century it has been renamed to System Z, or nowadays it's called Z Systems. And before that it was named Z series, so the numbers have not continued. It's important to see that this system switched from 24 to 31-bit. Now you could ask why 31-bit? Usually in computer science we have 32-bit. The answer is that, of course, it's a 32-bit system, but the most significant bit is used for indicating whether it is a 24-bit instruction for backward compatibility or a real 31-bit instruction, so it's sort of not usable for addressing. And that is why it's called, in fact, a 31-bit architecture. And then later on, with the introduction of the Z systems, it has been further developed to a 64-bit architecture, which it is today. And the most recent current generation of the Z processor is the version Z14. That's the newest one. So approximately every 1.5 to 2 years, there's a new generation of new processor generation in average. So it's not always exactly, but it has evolved like that. So still the architecture is backward compatible, and even the most modern Z14 would execute a program written for the original 24-bit S360 architecture. The CPU is a so-called extreme CISC processor, so it has a very large instruction set of machine instructions. And the current CPU now is the newest generation is a 10-core CPU. Every CPU is called a processing unit, a PU, or every core is called a processing unit. And on a CPU chip, we have 10 cores plus the caches, and these are put together on a single chip module. These chip modules may look like this. This is from a set 13, but the new ones are, of course, not very different regarding the visuals. The current CPU has a clock rate of 5.2 gigahertz, so it's a very high clock rate. And the PUs of such a system can be configured for different workloads. This configuration is done in firmware, so it's not that it's a different CPU or different physical thing, but it's just done by software. So the CPU can be configured to execute different kind of workloads. Some are so-called CPs, general purpose processors, that execute everything. They execute ZOS, Linux, and all kind of programs. But there are also special purpose PUs, like for example the IFL, the Integrated Facility for Linux. This is a PU that just runs Linux and its applications. Of course, this is only sort of prohibited by firmware because the physical CPU is the same. But this allows IBM to license these CPU cores with a different, much more cost-effective price, for example. So it's basically an issue of licensing and pricing. Also, there's a special kind of special purpose CPU for Java-based workloads, like for example the WebSphere application server, which is called ZIIP. So this is a PU that is only configured for executing Java and other modern, so-called modern workloads that are not classical CISC COBOL programs, for example. Nevertheless, it's physically the same processor type or the same architecture. On the right-hand side, you see the setup of the registers of the mainframe PU. Of course, every PU has an arithmetic and logic unit, an ALU, and a control unit, which is more or less the case for every processor. And then it has a set of registers that are typical for the mainframe CPU. There is the so-called program status word, PSW, which is containing the full state of the currently executed program. So it has two parts, the flag part and the address part. So the address part contains the program counter, the actual address that is executed, and the next address that needs to be executed. And the flags contain a status like, for example, overflow, division by 0, and things like that. Then we have 16 general purpose registers and also 16 floating point registers. And the width of the registers is different in this picture. A single yellow block indicates always the width of the architecture. So for example, on a 31-bit or 32-bit architecture, the PSW would be 64 bits together, address and flags, and the general purpose registers would be 31 bits. And in this example, for example, the floating point registers have double the machine word size. Okay. On the right lower corner, you see the access registers. There are 16 address registers, and these are used for they were introduced for the ESA architecture, which is an extension of the original XA architecture with 31-bit to increase the size of available virtual memory for an application without increasing the address size. Additional data-only address spaces have been introduced, and for each of these virtual data-only address spaces you need, of course, base register for addressing, and these are the access registers, roughly. Okay, so this is the basic structure of the CPU, and it's important to note that this type of processor is an extreme complex instruction set computer, and this means that it has complex instructions for example, load and store operations, for different kinds of conditional branching, for encryption, for string manipulation. So there are machine instructions that are nearly like a complete library routine on another platform. Okay, so string manipulation, counting characters and things like that. So these are very complex instructions. Many of them are not actually directly implemented in microcode, but they're partially implemented in something called minicode, which is again calling them microcode instructions. So it's a multi-layer hierarchy of instructions. And many of these instructions are actually implemented in the CPU in software. But from a developer's point of view, of course, they are machine instructions. And of course, we have different instructions for switching or for the different address sizes, 24 versus 31 or 64-bit. This comes or originates from the history and evolution. So many of these instructions are just twice. Many similar instructions are available for 24 and 32-bit or 31-bit. And of course, this also increases the size or the number of instructions. A very unique feature of the mainframe CPU is the existence of hardware machine instructions for processing or calculating numbers in the so-called binary coded decimal scheme, which is very important for commercial calculations, which is one of the core domains where the mainframes are used. And this allows to make decimal calculations with a defined precision. And usually digits are represented by 4 bits or 8 bits in sort of kind of a digit string. And in the packed format, you have 4 bits per digit, so 2 digits per byte. And with these packed decimal instructions, the system can calculate directly by machine instructions. So there are, for example, machine instructions for BCD addition, BCD division, and so on. And since the Z13, there have been further instructions added, for example, for so-called single instruction multiple data instructions for fast string processing, which is important for example, speeding up string manipulation for non-structured data and things like that that might be used, for example, for improving Java performance. So it's very common that for the mainframe architecture, for every generation of the CPU, instructions have been added to address specific needs and specific problems of that era or that period of time. In general, of course, we have virtual memory management, which is an important functionality of a CPU. And this is done by multiple step indirection. You can see it here. This is, by example, the original structure from the S360. So it's a 24-bit structure. Every virtual address is interpreted in 3 parts: a segment, a page, and a displacement. And the segment points to a number in a segment table, which again is indexed by the so-called segment table origin register in the CPU. And inside that table, there is another address that points to the so-called frame number, which then it points to the page table and then points to the frame number, and then the displacement is indexing it in a memory page. So this is the way how a virtual address is translated to a physical address somewhere in memory. That was the way how it was done in the original architecture, but part of this idea is still present. For example, the 12-bit displacement is still in use, even with larger addresses. So every memory block has 4 kilobytes. This leads to a certain layout of the virtual address space, and it's shown here. So in the original S360 architecture, every virtual address space was at a maximum 16 megabyte. The nucleus, the kernel code, was residing at the low edge, starting from 0 address. Then there was the region of the virtual address space. The region is actually the memory that's available to the program, the heap and the stack and so on. And then we have some address spaces that are reserved for mapping in shared libraries, and these are or other address information that is sort of common for multiple address spaces, like for example the system queue area, where some global control blocks for all parallel programs for all address spaces are maintained, the pageable link pack area for libraries, and the common service area for example, implementing inter-process communication between address spaces. And then, of course, we have the so-called local system queue area, which is present in every virtual address space separately and contains the program-specific control structures that are needed to communicate, for example, with the kernel. These are especially device control blocks, task control blocks, so control structures that are needed to, for example, control I/O operations. In the modern architecture, this evolved a little bit due to the larger address size, and to keep the system backward compatible. Everything was sort of doubled in the address space, and the nucleus was pushed around the 16 megabyte border. So we have an extended nucleus for the 31 or 64-bit applications and the nucleus code for the 24-bit applications. And we have also basically two regions for depending on the type of addressing. Of course, it can happen that you have a program that links a 31-bit or 64-bit program that links a 24-bit library. So you could have also in one process switching between these. And this means that both needs to be present in parallel. Okay, so this was a short introduction on how the CPU is built up, how the address size increased over time, what this had, or which kind of consequences this had for virtual address management, and which registers are there, and what is typical for the machine instruction set of that type of CPU, of the mainframe CPU architecture. Thank you very much.